Okay, so I will go to 1.2 here. So affine orbifold is a orbifold geometric structure model on this affine geometry. So I talked about some parallel end, but I didn't really introduce what this end was. So please skip that. I will move this somewhere else next time. But we will do the affine suspension. So these are the some affine subspace is a dense open subset, which is a complement of n plus one dimensional space. So this should be some n here. Sorry, it should be complement n dimension, and so affine transformation is some restriction of some projective automorphism acting on this RPN. Sorry, this is Rn plus one, so it should be this is correct, and this is n dimensional, and Fr plus is isomorphic to projective automorphism acting on Rn plus one by restriction homomorphism. So dilatation of the affine transformation is a linear transformation with respect to some affine coordinates, so that eigenvalues are always bigger than one or less than one. So in this case, when I say linear, it means there's some fixed point, and which is considered as the origin. And then gamma is an expansion map in the dynamical sense, and scalar dilatation is one where the eigenvalues are the same. Okay, and uh, actually, it is some multiple of some identity map, so it has to be some multiple. So affine before this radian, if it fixes a point in Rn plus one, and the holonomic homomorphism is like this, and the real projective orbifold dimension n has a developing map here, and the holonomic homomorphism like this. So we regard Sn as embedded unit sphere in Rn plus one, and we obtain the radian affine manifold by taking O tilde and deb and h, and so we define this by sending xt to t deb prime h. So we develop into this unit sphere, and um, so we can consider Sn as some unit sphere here, and then you can extend this. You can define this new developing map by sending x to tx prime, and so for each element here we can define a deck transformation here by sending it to gamma x, but you use this norm here, which is given by h times t dep x, and then for the homomorphism going to r plus. Okay, so there's a choice here, so you can use this many type of theta. As long as this is like this homomorphism, then you can multiply by this, and then there is a transformation sending this to this, sending x2 to s times t for each t. So we can quotient by O times r plus s rho and this group here. So pi 1 x will act by this map, and then this is an affine orbifold with a fundamental group isomorphic to pi 1 of O times c, because I added this rho s rho, and the s rho is actually commutes with any other element. So therefore, so s rho is just a scalar multiplication by rho here. Rho is some number, and rho can be some bigger than one number, and so so the homomorphism is given like this, and so then the quotient is called the affine suspension of O, and it is of course a radian affine manifold here. And the special affine suspension is a suspension where theta is 1. And the variation is called generalized affine suspension. Then we deduce that it is an affine orbifold with fundamental group isomorphic to this. Okay. So given so when you denote by S C sub O tilde the manifold O times R with structure given by D prime, we say that it is C O tilde is affine suspension O tilde. So in this case, there is no group. And in these cases, you can also do some one parameter family of dilatation. So these are just the scalar multiplication, and so there's a family of self-diffeomorphism of orbifold M lifting to this. So if M was constructed like this, then you can always find for any dilatation map like this. And it's called the group of radiant flow diffeomorphism. And if O is a strongly tamed real projective and orbifold, then the affine suspension will always admit this radiant diffeomorphism because this construction will always. I mean, this row is I mean scalar multiplication, and then you can do act by any other scalar multiplication, and it will lift. So conversely, if you the radiant flow diffeomorphism where all the orbits are closed and have the same homology class, then this is actually a radiant is obtained from radiant affine suspension construction, and from a real projective structure on O. So this construction always comes from some real projective structure, and you obtain affine structure here. And proof of that I will have to skip here. Okay. So we'll go over some linear algebra. So 0.3 is a linear algebra, and so given an eigenvalue lambda of G, so C eigenvector is a non-zero vector in the kernel of this. So you have to take the kernel of the eigenvalue, but also its conjugate as well. And then you take the intersection. And C fixed point is a direction of C eigenvector in RPN. Okay, so this is more general, and so it's not a fixed point in general. Okay, and so if you have any primary decomposition, so primary decomposition is something you will have to have learned. It's just so you can write any minimal polynomial of G as powers of x minus lambda I gamma I for these are the eigenvalues, and you have to multiply with some multiplicity. And so if you look at the kernel of these things, so there's a unique way to write this, and then these Cn will be direct sum of these. And the real primary subspace is you have to sum with the conjugate subspace, and then you take the intersection. So a vector is affiliated with norm and the mu of an eigenvalue if vector is an R mu C. So these are the ones which have are in the direct sum of these intersected by n. So I think there should be some parentheses here, but I forgot these. But so anyway, so not the intersection and then taking the direct sum. So if you have a distinct norm of eigenvalues, then these are Rn's direct sum like this, and this is not zero if mu equal to lambda bar for at least one lambda. So application of this is that if you have a G in here and B and W are some complementary subspace, and every norm of eigenvalue in one direction of B is stronger than any norm of eigenvalue in the direction of W, then the PS is subspace that is a join of C eigenvalues of C. Then then if you take any general points here in the complement, then it accumulates only to this eigenvalue space as n goes to infinity. And if there's any neighborhood of x in here, then and there exists an open subset where each point is realized as a limit point of some subset. Okay, so this what this means is that so if you have a stronger eigenvalue back values than for b w v than w, then you can always, if, and this is relation strict, then whatever gn will x will accumulate to only those points. But these should be in the C eigenspaces because the cyclic space has a lower contribution. Okay, and this one just means that each point of the this is has to be realized because it has the same strength of the eigenvalue. Okay, so those are some dynamical results. And next thing I talk about is a nilpotent and also potent group. So first of all, you can talk about is Iwasawa decomposition. So if you write any matrix, you can write it as a K G times AG times NG in orthogonal system. So orthogonal means that this Rn plus 1 is written as as some orthogonal coordinate. So these are all written in orthogonal coordinate. And uh, and then AG is positive diagonal element, and is near matrix, near unipotent, and diagonal ones are norms of the eigenvalues of G as element of ON. Okay. So of course, this AG does depend on the orthogonal coordinate system. So it means that you can choose an orthogonal coordinate system so that this happens. Okay, is so the diagonal elements are the norms of eigenvalues. Okay. So this, of course, this orthogonal system does depend on G. Okay, so that's one thing you need to. So of course, this proof is kind of long, but this fact itself, Iwasawa decomposition is very easy. It's in the standard books like Helgeson, but of course, they don't have this property like what I said here. So this is different. Okay, so it's a very long proof. I will skip this. And so next, I want to talk about the maximal unipotent subgroups. And so we define this to be all the conjugates of unipotent group, and then you take the union. And then you can also think of it as all the conjugates of U under SNN plus 1. So this is because any unipotent group is conjugate by element is still unipotent, and the unipotent group is characterized by a maximal flag, and any maximal flag is conjugate to lower triangular unipotent group by orthogonal element of ON, because ON plus 1 will act transitively on the maximal flag space. Okay. And the next corollary we might need is that if the eigenvalues satisfy these conditions, so the largest and the smallest one are in some compact interval defined by C, then then this G is always in the uniform bounded distance from U prime in the Lie group sense. Okay, so I will and so subset of a Lie group is polynomial groups if the volume of BR radius are less than or equal to a polynomial of R. So you intersect the subset with the ball of some radius, and then the volume is not growing. Maybe I should say some set with open set. Maybe it might be better to say that. And then then is less than equal to some polynomial, then of course the metric here is given by standard left invariant bilinear form, and so this is, you can choose it to be invariant under conjugation by compact group On plus one here, and so you can show that U prime is a polynomial growth from the distance from I. Right. I will not prove it very much. Okay. And another important theorem is Jasenhaus theorem. So any discrete group, you have these. You can write it in this complex basis of this form. Then, if there's some epsilon that the order matrix A in G which satisfy this Eij minus one is less than epsilon. So this means that theta ij is very close to zero, with some uniform bound. Then it is contained in the radical of the group. So radical is subgroup with only eigenvalues. So suppose you say that all these theta i's are very close to zero, then it's always going to be zero immediately because of the fact that it is discrete. Okay, so there's some positive epsilon which only depends on the C and N, I think. And so also you want to talk about unit norm eigenvalued element if the eigenvalues has only norm one, and so on. And the orthopotent group is some group which there is a fixed flag of subspaces. So flag means that there is this sequence of subspaces, and so that this is dimension gets strictly bigger, and it acts. So if G acts orthogonally, so there's always an induced action of these induced subspaces. So these are vector subspaces. So then it acts as orthogonal. Then it's called the orthopotent. So the distal group is actually linear group which only increases norm of the vector. So this is a group where if you multiply, then length is always increasing, not decreasing. So of course, isometric group is always the one which preserves the norm. So it is an example of distal group. So distal group is actually autopotent. So we can prove that if G is a unit norm eigenvalued subspace, then G is also potent. And if G is discrete, then it's actually virtually unipotent. And if it's a connected Lie group, then it's an extension of solvable group by a compact group. That means that G mod S is a compact group or some normal solvable group S in S. And if G is contractible, then it's actually simply connected solvable Lie group. Okay. Okay. That's all that I'm saying, and I should say contractible Lie group, and this should work. And next, you want to talk about something called the dividing group. So suppose we have some domain and which is properly convex, but maybe not strictly convex. And if discrete group acts on it so that omega mod gamma is compact, then omega gamma is a induced orbifold structure by this proposition. So as long as we have discrete group and the action is isometry group, then automatically you get a orbifold structure. That's because this group is acts properly because of the discreteness and the properness. I mean, because it's isometry. So please see this, and the element is elliptic if it's conjugate to some subgroup here. And so if it's a properly convex domain and gamma is a projective automorphism, and if gamma is discrete, then the element is elliptic if and only if it fixes a point of omega, or it is of infinite order. Of course, I should say this is an open domain here, open domain. So so the proof is that basically, if you have any elliptic element, then you can uh, take the orbit. So it has a so you can show that this orbit is compact closure. So therefore, there's some fixed vector under this because this is a linear, and then you have some compact closure group in some cone. So therefore, you can find the fixed point. And so if it's fixed point, then it has a stabilizer group, and so since this is orbifold, it has to be finite, and so on. So combustive is finite, and certainly it's elliptic. Okay, so you can prove this. Okay, so fundamental definition of Benoit is that so you take any element and you write the sequence of norms of G with repetition by respective multiplicity. So say this is a decrease strictly not non-increase. I mean, it's a non-increasing one. You can of course repeat it, but this so the previous one cannot be bigger than the original one. Then lambda one is called spectral radius, and if the final and the first one is different, so if this is same, then this all has to be one because it's in SNR. And the element is proximal if it has a multiplicity one. So the lambda one has a multiple no other eigenvector with the same radius, and positive proximal if G is proximal and lambda one is the real eigenvalue. So it could be minor. This could be negative as an eigenvalue. So that doesn't happen. And so multiplicity one means that the eigenvalue has a multiplicity, and you have to sum all the multiplicity of the eigenvalues with same norm here. Could be, of course, complex. And positive proximal if G is proximal and lambda one is eigenvalue of G. So element is semi-proximal if lambda 1G or minus lambda 1G is an eigenvalue of G. Okay, and it's positive semi-proximal if lambda 1 is an eigenvalue of G. And positive biproximal if the G and both G inverse are positive proximal. Uh, of course, Benoit doesn't assume this, but we do. And G is called positive biproximal if both are positive proximal, and this is positive bi semi-proximal if G and G inverse are both positive and semi-proximal. So of course, proximity is a stronger condition than the semi-proximity. And we can also define what's called the attracting fixed point and the repelling fixed points, whereby A is the eigenspace associated with largest eigenvalues of G, and R is the eigenspace associated with the smallest eigenvalue of G. So for the by semi-proximal element G, here so then this is both going to be identity maps. And AG. So I guess right. I guess space. And then the AG is associated with lambda one, and the IR is associated with lambda n. So AG is called the attracting fixed point and the repelling fixed point. And if G is a positive biproximal, then and then we denote by BA so the factor in the minimal polynomial, for the M is the multiplicity of the eigenvalue in the characteristic polynomial G. Then the and PR is this vorticity, then you can always show that these are actually in these subspaces. Um, so X properly, then so if you have any non-identity projective option acting on properly convex domain, then it is positive by semi-proximal. So that's proven in here. Of course, here I have to assume that the eigenvalues are bigger, largest eigenvalue and the smallest eigenvalue are different, then you get this. Okay, so suppose that omega is a properly convex domain and if infinite order X with only single norm of eigenvalue, then actually you can show that there's a so infimum of the distance that it moves is actually zero. Um, so the way I prove it is to show that there is some fixed point, and then I have to blow this fixed point action, and then I show that they are essentially same as a linear map, and then we have to reduce this to transversal direction, and then we have to do the inductions and so on. So that's how we will get this. And right, so if you have this properly convex domain and omega mod gamma is compact, and this is discrete, then this is a divisible action. Then if G has two distinct positive eigenvalue associated with Q, and the smallest and the largest values are bigger than one or less than one, and is positive semi-proximal. Because I mean so this holds because if there cannot by compactness there cannot be very I mean the infimum cannot go to zero. Okay, so you can show that. And if G is not also potent, then cannot be also unipotent. Okay. Right. So G cannot be also potent because its eigenvalues has to be different, right? So theorem of Benoit is that if omega is a properly convex, not necessarily strictly convex, it's compact and Hausdorff, then gamma is positive biproximal with the following properties like this, and the dimension will go like this. Okay, so I think I will end here, and then I will go to higher convergence group uh, from next time, and then I'll do 1.4, then try to do up to chapter 3 here, chapter 2. Okay. Okay.